Okay, in this second video, we're going to add some more things to your picture here. So on the back of your picture or on a separate page are the questions that go along with this. So let's look at where we are in the questions. So number 1, it says a physics student goes bowling. We did that. We went bowling. Number 2, a physics student drops a bowling ball from the top of the cliff. We did that. Number 3, a physics student goes bowling off the top of the cliff by firing the bowling ball horizontally. We did that. All right, so we're going to jump down to number 5. Draw arrows on your graph to show how the horizontal and the vertical velocity components change over time. So the horizontal velocity, I'm going to write it as Vx because it's happening in the x direction. And the vertical velocity component is going to happen in the y direction. So we want to look at what I call the Vx and the Vy arrows. These are the components. These are the same components that we're putting in the component chart when we were doing vector addition using the component method. So what do these component arrows look like and how do they change over time on my graph? So we did 2 examples. We fired the bowling ball 20 meters per second, and then this one over here is the 40. We're going to go back and use this 20. So when I fire the bowling ball with 20 meters, or I go bowling with a velocity of 20 meters per second, I write that on my picture like Vx equals 20. And then I put an arrow like this. That means that I'm going to fire the bowling ball off the cliff 20 meters per second. And the key takeaway here is that the Vx arrow never changes. It's going to stay 20. So I'm going to draw the same length arrow all the way down and say Vx equals 20. Vx equals 20. Vx equals 20. Vx equals 20. How do I know it doesn't change? Because Vx equals 20 is constant velocity. And if it's constant velocity, it's going to stay the same all the way down. So let's just say that the Vx arrows stay the same. One of the questions here in our notes says sketch a graph of the Vx arrows versus time. So this would be the Vx arrow versus time. And I'll say it stays the same. It stays the same. And in my example, the Vx arrow was 20. And it stayed the same. Now let's look at the Vy arrows. The velocity in the y direction does not stay the same. So I have to go back over here and I have to pretend that I'm dropping the bowling ball. When I pretend that I drop the bowling ball, the initial velocity in the y direction, so I'm going to put a little y there, and I'm going to put a y here, because this equation then allowed me to calculate the distance that the ball fell in the y direction. But the initial velocity in the y direction is 0. That's why I X'd that out. So that means up here at the top of the bowling ball, there is no y arrow. So I'm just going to write down Vy equals 0. But now, 1 second later, when my ball was over here, there is a little teeny Vy arrow. How do I know that? So I'm going to write that down here. I'm going to write down Vf equals Vi plus At. We know that the time it takes to fall straight down and parabola down is the same, so that this equation, I can still look at the dropping to represent the parabola, and the Vi in the y direction is still going to be 0, so I'm going to X it out. But this will tell me the final velocity in the y direction. So the final velocity in the y direction is going to be equal to 9.8 times the time. So I just ask you how fast the bowling ball was going after 1 second. And it's going 9.8 times. It's going 9.8, which makes sense because something goes 9.8 meters per second faster every second. So that means the final velocity in the y direction after 1 second is 9.8. So this here is V final in the y direction equals 9.8. So the Vx arrow is 20. and the VY arrow is 9.8. So if you want to know how fast the bowling ball is going right here at 1 second, you can parallelogram method those X and Y components, and you can find the velocity of the bowling ball. After 2 seconds, I'm going to put a 2 in here. 9.8 times 2 is 19.6. So this one is 19.6. That's the VY arrow there. After 3 seconds, we know the VX arrow stayed the same, but the VY arrow, 9.8 times 3, is 29.4. So, whoops, yeah, 29.4. So the Y arrows are getting 9.8 bigger every second they fall because of this equation down here, 9.8 meters per second faster every second. So the VY arrows keep getting longer and longer. So I'm going to graph those out. So the VY arrows over time, they start at 0 and then they get bigger and bigger and bigger and bigger. And if I actually found the slope of that line, it would turn out to be 9.8. They get 9.8 bigger every second. All right, so we did that one. Number 7, what would happen if you rolled the bowling ball twice as fast? It landed twice as far. It landed 100 when I rolled it at 20. It landed at 200 when I rolled it at 40. So we had already done that one on the other picture. All right, we have one other one to do then. It says, what is the velocity of the bowling ball after 3.5 seconds? So I'm going to go back to my picture, and I'm going to try to figure out where I think 3.5 is. So this was 1 second, 2 seconds, 3 seconds. This is 4. So I'm just going to guess about right there. What do I know about 3.5 seconds? I know that the VX arrow remains the same, so it's going to be a 20. And the VY arrow, I can find the VY arrow, VY. It ends up being 9.8 times however long it was falling. So 9.8 times 3.5 turns out to be, I don't know, I didn't do that. All right, so we have 9.8 times 3.5, and we get 34.3. So this is a 34.3. So how do I find the velocity of the bowling ball right here? I'm going to parallelogram method these like this. And then I'm going to do the hypotenuse. I'm going to call it C. Now, I am not saying that the ball arcs out like this. I am finding the velocity of the bowling ball right there at that dot. But the velocity at that dot is equal to C, which is the resultant velocity. So I'm just going to do a little Pythagorean theorem. So we'll square that, plus 20 squared. And the velocity of the bowling ball is 39.7. So we'll write that down, 39.7 meters per second. And I notice that the bowling ball is not falling straight down. It's kind of like arcing down at an angle. So I'm going to call this my descriptor angle. And so we'll call that tangent. And that would be opposites. That's going to be 34.3 over 20. So 34.3 divided by 20, we'll inverse tan that. And 59.8, we'll say. So it's coming down at 59.8 degrees. And I kind of picture this being like a little XY grid. And then I could call that 59.8 degrees south of east is how it is arcing in the parabola at that exact moment there. All right, so I know our notes look a little bit messy here, but all of the key things that you need to know are in this picture and are obviously summarized on this piece of paper here. So the homework assignment that goes along with this lesson is a WebAssign. And the WebAssign has problems, projectile motion problems that are fired horizontally, anything that goes straight. Some of the WebAssign problems are fired at an angle, and that's the next lesson. So just know that the WebAssign has two different kinds of problems in it. So let's go over a problem when something is fired horizontally. And so I call this my tiger example. So let's look at the tiger example. I'm actually going to switch and do it on lined paper so that I can draw it bigger for you here. All right, so it doesn't matter what the problem is. There's going to be a cliff, a tall building, a table, a high rock. There's got to be something up high. All right, so this one says a tiger leaps horizontally from a rock. All right, so you know what? I'm just going to draw my rock like a cliff. All right, so I draw my cliff or my building or my rock, and it says that the rock is 6.3 meters high. So I'm going to write down D equals 6.3 meters. But I'm going to make one little change now. I'm going to put a Y on there because that's like the height in the Y direction. All right, he leaps with a speed of 4.1, but he leaps horizontally. So he's going to come off the rock like this. So his velocity in the x direction is going to be 4.1 meters per second. We're always going to have a Vx and we're always going to have a dy. One thing about these problems that makes them kind of easy is that they're all the same. They're all the same. All right, so when he leaps off, he's going to projectile motion to the ground. And he's going to land a distance over from the cliff. So the distance over is going to be called dx. dx. That's why I need to have a dx and a dy, because I'm going to have two different distances. And when I say over from the cliff, we've kind of made an assumption that this is like from the base of the cliff. All right, letter A says, how long will it take the tiger to reach the ground? We are always going to find the time to reach the ground like this. D equals 1/2 AT squared. Why am I using that equation? Because it's this. I don't know how long it takes the tiger to do this, but I know that if he just fell straight down, then I could use this equation and the initial velocity would be 0 because he's falling straight down, and it turns out to be, again, the dropping equation. D equals 1/2 AT squared. So D equals 1/2 AT squared, and I'll put the Y here. So this is 6.3, this is 1/2, this is 9.8, and T squared. So how long is it going to take my tiger to reach the ground? So that's going to be 6.3 divided by 4.9, and then we'll square root that, and 1.13 seconds. He's going to hit the ground in 1.13 seconds. All right, the next question. How far from the base of the rock will he land? How far from the base of the rock will he land? How far over is he going to land? He's going to land right there. So what makes him go over is how fast he leaped. And I know that in the x direction, he leaps with a constant velocity. So because he leaps with a constant velocity, I'm going to use the constant velocity equation. So I'm always going to use velocity is distance over time, but this is happening in the x direction. So I'm going to put little x's on there. So how fast is he going in the x direction? 4.1. I'm looking for how far over he goes in the x direction. And then the question is, how long is he in the air? How long is he arcing over? Well, we know that the time to arc is equal to the time to drop, so that's 1.13. So how far over does he go? That's going to be 4.1 times, so whatever I have on my screen, so 4.65 meters. 4.65. I hope I didn't make any algebra mistakes. All right, the last one is the little trickier one, and I wish I didn't write this here. I wish I wrote this like up there. All right, calculate the tiger's velocity right before hitting the ground. All right, so right here, That's why all this stuff's in the way now. All right, so when he hits the ground, he has a velocity that has an x component of 4.1, but he also has a velocity that has a y component. And the y component, again, I'm getting with this equation here, I'm going to pretend that he was just dropping off the rock. The initial velocity would be 0, and his y component is going to be equal to at. So the vy is going to equal at. So a is 9.8. How long was he dropping? 1.13. And that makes sense because he goes 9.8 meters per second faster every second that he drops. So 9.8 times 1.13 is 11.07. So 11.07. So I have a 4.1 in this direction. I have an 11.07 in this direction. So I'm going to parallelogram these, parallelogram method. And then I'm going to do the hypotenuse. And the hypotenuse that I'll label C. C is going to be equal to the resultant velocity of the tiger right when he hits the ground. So we'll square this plus 4.1 squared, and then we'll square root that. And how fast is he going? 11.81. 11.81 meters per second. And again, I need a descriptor angle. So maybe I'll pick this one. And I can use tangent of that is 11.07, opposite over adjacent. And so 11.07 divided by 4.1. Second tan, second answer, 69.68, 69.68, 69.68 degrees. And again, if this was a little grid here, like an XY grid, I could call that south of east at that moment. Every single problem on the WebAssign that is fired horizontally is done the same way. That's how you get the time. This is how you figure out how far over it goes. And if you need the velocity, you got to figure out the components, and you have to do vector addition. All right, I hope that helps get you started, and we will play and practice some more the next time I see you in class.